Let's get going again. We talked about glucose and some important things about its structure. I want to introduce two other carbohydrates that I expect you to know and be able to recognize. It's best if you memorize these by their relationship with glucose. So mannose is found a lot in carbohydrates in biology. And mannose is the C2 epimer of glucose. So I'm just going to show you the cyclic hemiacetal form. And if you want to go back and this is, I guess we're doing question 1 on your quiz. If you want to go back and practice drawing the open chain form and going back and forth between those two, that's probably a good idea. Mannose is the C2 epimer of glucose. So that means we're going to keep everything about glucose the same, but we're going to switch the stereochemistry at C2. We're going to start by drawing the alpha anomer. That means at carbon 1 and 5, the hydroxymethyl group at C5 and the hydroxyl at C1 need to be on opposite sides of the ring, up and down, trans. Then remember, C4 at glucose is down, C3 is up, equatorial. In glucose, C2 was like this, so in mannose, C2 needs to be straight up. And if you want to redo that line in the back and make it sort of broken so that it's clear that this one's in the front, that's what makes mannose different from glucose. So we would call this molecule alpha D mannopyranose. The pyranose would tell us it's a 6-membered ring. The mano would tell us what the configuration is at C2, C3, and C4. Alpha tells us what the configuration is at C1 relative to the configuration at C5, and the D gives us the configuration at C5. So that's alpha D mannopyranose, and then I'll leave it to you to draw what the beta anomer looks like, but that's just going to be the diastereomer where the OH is equatorial. So that's probably useful as practice. You should go and do that. The second sugar, the second carbohydrate, or rather the third, in addition to glucose and mannose, is called D-galactose. And if that sounds like galactic, that's on purpose. It turns out our term galaxy comes from the Greek for milk because of the Milky Way. And galactose is a carbohydrate that's found in the milk oligosaccharide lactose. And we'll talk about that in just a little bit. Galactose is the C4 epimer of glucose. So to draw galactose, you start with glucose, and again, we'll just do the alpha anomer, and I will leave it to you as an exercise to draw the beta anomer. Everything needs to be in exactly the same place as glucose except for C4, and at C4, whereas in glucose the stereocenter was a down OH group, at C4 it's up. So you can recognize galactose because C4 will have an up axial OH group. The term galacto refers to the configuration at C2, C3, C4. The letter D refers to the configuration at C5, and then the Greek letter alpha refers to the configuration at C1 relative to C5. In other words, these two groups at 5 and 1 are trans to each other in the alpha diastereomer, whereas they would be cis to each other in the beta diastereomer. All right, glucose, mannose, and galactose. There are other carbohydrates other diastereomers of glucose, but these are the ones we're going to worry about. The other ones are not quite as common. All right, So you should have those memorized. If I point to a carbohydrate and say, hey, what sugar is that? You should say what it is, whether it's glucose, mannose, or galactose. There are some other carbohydrates that we'll talk about occasionally. They'll show up in some example problems in your problem set, but I will always explain what they are. And I don't think we necessarily need to talk about them now. All right, let's do some polysaccharides. All right? So, and that's not how you spell saccharide, is it? There's two C's, something like that. Okay. So it turns out that, as you know, glucose has an open chain form that's an aldehyde that is reactive. But it turns out that there's other, and the aldehyde can react with nitrogens to form imines. But it turns out that carbohydrates can also react with each other. And the way this happens is usually as follows. It turns out that this OH is going to be a leaving group, and the ring oxygen is going to be a kicker-offer. So you've seen elimination reactions before. You know that when there's a lone pair adjacent to the leaving group, the lone pair can kick down and the leaving group can leave. Now in this case, as it's leaving, it probably picks up a proton from some source, probably water or some other group. When that happens, you generate a kind of weird intermediate. Oops, that looks like this. The oxygen has a positive, the ring oxygen has a positive formal charge on it. The leaving group, water, left, right? And this intermediate is called an oxonium ion. It is even more reactive than an aldehyde. And the reason it is even more reactive than an aldehyde is because it's just like the aldehyde, only the oxygen's positively charged. You would expect this oxonium ion to have a resonance structure that would look like this, where we move the pi electrons from the carbon-oxygen pi bond out to be a lone pair on the oxygen, leaving a full positive charge on what used to be the carbonyl carbon. So oxonium ions are highly reactive. And of course, water could attack and come right back on, and that would take us right back to the starting material. But you could ask, what if, before water comes back in and attacks, what if one of the OH groups from the sugar, from another sugar molecule, acts as a nucleophile? Yeah. I am. Prayers answered every day.
Oh, yeah.
Yeah. Okay, so what if one of the alcohols from another carbohydrate acts as the nucleophile? Let's just pick this one that I'll highlight in purple. Okay? Supposing that one acts as a nucleophile. What will likely happen is a base, possibly water, will attack and deprotonate that alcohol while it's attacking the oxonium ion. And you can attack either of the two resonance structures. I could attack the positive charge, or I could attack this one, and if I attack the one on the left, I need to break the pi bond and put those electrons up on to the carbonyl oxygen. These are both acceptable options. When I do that, I've got two possibilities for the stereochemistry at C1 of the electrophile. So we'll call this the electrophile, and this the and then this one over here, the nucleophile. And this is C1, 2, 3, 4, 5, and 6, and this is C1, 2, 3, 4, 5, and 6. All right. So the C3 hydroxyl from the nucleophile is attacking C1 of the electrophile, and it can do so either to give me a beta configuration at C1 of my electrophile, or alternatively, it can give me an alpha configuration. All right, so this is the option if I get the alpha configuration. And this is the option, I said that entirely wrong. Is this oxygen on the same side or the opposite side of the ring as the C5 hydroxymethyl group? Same or opposite? Same. This one's up, this one is up. So that's a beta configuration at C1. The other option is to get, this configuration. And now the C1 group, they're on opposite sides, so this is the alpha configuration. Okay, those are two disaccharides. This is certainly one of the things that happens when you go to caramelize sugar. And the only difference is that any of these alcohol, we've only done one step, any of these alcohols are still available to be nucleophiles in these types of reactions. And so in sugar caramelization, you end up with an uncontrolled mixture of linkages between sugar molecules. The linkages that we have just talked about are called glycosidic linkages. And they always involve what used to be the hemiacetal carbon. The hemiacetal carbon used to be bonded to an OR group and an OH group. Now in these disaccharides, for the carbohydrates on the left, the hemiacetal carbon is no longer bonded to an OH and an OR group, but to two OR groups. That functional group is called an acetal rather than a hemiacetal. And another word for that is a glycoside or a glycosidic linkage. We have to have a specific way of talking about glycosidic linkages that tell us which anomeric carbon or which formerly hemiacetal carbon is connected to which OH group from the other carbohydrate. And that will tell us whether the hemiacetal carbon, the blue carbon, is in the alpha or the beta configuration. So the way we do this is we'll describe this glycosidic linkage, and I'm talking about sort of this linkage between the two sugars. We're going to describe this with starting with the configuration of the anomeric carbon or the or what used to be the hemiacetal carbon, which is beta. Then we'll write down the atom number of that anomeric carbon, which in the case of glucose is always 1. Then we'll draw an arrow and we'll write the number of the hydroxy group on the next sugar, the one that's attached to the anomeric carbon. So the acetal carbon, the one that used to be the hemiacetal carbon, we will call that, as I said, the anomeric carbon. And it is linked to the C3 hydroxyl of the next sugar. So we will call this a beta 1,3 glycosidic linkage. Over here, the glycosidic linkage is alpha 1,3. All right, questions about how you do that? Yes?
Can you explain again why the alpha is alpha? What we said.
The thing that makes this linkage alpha is you got 2 OR groups attached to the same carbon. That makes it an anomeric or acetal carbon. Then you look at the thing that's coming off the ring on C1 and you compare it to the thing that's coming off the ring at C5. And you ask, are they on the same side or opposite sides of the ring? The C5 group is up. The group on C1 is down. They are trans to each other, which is why we call it alpha. If they were cis to each other, as they are over here, we call it beta. Yeah?
Would you want us to always draw it in the chair conformation?
You don't have to draw it in the chair conformation. Yeah, go ahead.
So that one's alpha 1,3. Could it be like alpha 1,4 or alpha
Yep.
1,2?
Yes, you're seeing there's a ton of different independent combinations, right? It could be beta 1,3, beta 1,2, beta 1,4, beta 1,6. It could be alpha those as well.
And in a longer polysaccharide, like you could have all different types of those.
That's right.
Is it Nabon? What are those called?
Those are, we just call glycosidic linkages.
Okay, so
Yep.
it could be different linkages.
Yes. Could be all kinds of different linkages. And therefore you can see we've just drawn disaccharides, but I've only given you 2 of the various possibilities. And these are just for glucose dimers, right? I have drawn you 2 glucoses linked together, beta 1,3, but I could also draw 2 glucoses linked together, beta 1,2, beta 1,4, beta 1,6. I could draw 2 glucoses linked together, alpha 1,3, but I could also have done alpha 1,2, alpha 1,4, and alpha 1,6. And of course, if you're just doing this in a pan on your stove, it's going to happen in a lot of different ways. A single glucose, the hydroxyls on a single glucose might be involved in glycosidic linkages with multiple other carbons. So I've asked you to just, in your problem set this week, draw a complicated polysaccharide containing at least 8 sugar units with a mixture of how they're attached, alpha and beta, and which atoms are attached. If you're struggling to get started on that, talk to one of the TAs or me, and after you draw your first linkage and say, is this reasonable? And we'll say, sure. Now for the next one, make it different. You can draw one where a single sugar has multiple of its OH groups attached to other anomeric carbons, or you could draw just a linear chain where one anomeric carbon is attached to one OH group and then the next anomeric carbon would be attached to the next hydroxyl. But this is what goes on when you do caramelization of sugar, when you go make rock candy or peanut brittle or any other thing that's based on heating sugar. Yeah?
So will it always be the number 1 on the first number, or could it be different?
Will it always be the number 1 on the first number? Yes, if it's glucose. If it's fructose, fructose's reactive carbon is C2. So I should show you the structure of table sugar. Table sugar is a disaccharide. It's called sucrose. And sucrose involves one glucose molecule. And the configuration of C1 is alpha. And then I should have written this down because I'm probably going to get the configuration of the next stereo center wrong. Let's see if it's in my notes. Dang it. See if I can get it. Don't want to tell you guys wrong stuff. Okay, so nope, that wasn't right. Try that again. All right. Sucrose is kind of weird because over here you have glucose. And then over here, this is a different view of a sugar you've seen before. This is fructose. And in the glycosidic linkage between glucose and fructose, the two carbons that are linked together are actually both anomeric carbons. In the glycosidic linkages that we did before, one side was the anomeric carbon and the other side was just an OH group, was just from an OH group. Sucrose is different because this carbon 2 is bonded to two OR groups, just like carbon 1 is. On the side of sucrose, the configuration is alpha because this group is on the same side as the C5 stereo center, as the C5 substituent. And on the other side, on the fructose side of things, the configuration is, notice they're on the C2 substituent is on the same side of the ring as the C5 substituent. So it's actually beta on this side. So the linkage between glucose and fructose, I think you would call alpha 1, beta 1, glucose, fructose. This is table sugar. And when you heat it up, it likely goes back to its component sugars by a similar sort of reaction that we saw earlier, where this oxygen will be a kicker-offer and kick off fructose as a leaving group, and it will probably get protonated as it leaves. From that point, the individual monosaccharides can then proceed to form additional glycosidic linkages with each other. Yeah?
So for the fructose 2 is the hemiacetal carbon?
So in fructose, this is the anomeric carbon, yeah.
Anomeric,
Yep. Okay. So that's table sugar. Let's show you galactose. No, actually, let's show you lactose, but we'll show you actually human milk oligosaccharide, which has lactose in it, but an additional sugar that's kind of interesting. This weekend, we watched my baby niece for a lot of the day on Saturday. It's kind of fun because Amber's younger brother is like 8 or 9 years younger than her, and he got married a little bit later than we did. And so my kids are basically almost all grown, and his are like 4-year-olds and younger. So we sort of get to pretend to be grandparents with our nieces and nephews. And so we watched this little baby on Saturday, and it was fun. Taking care of teenagers is a lot different than taking care of a baby. A baby's more physically intense. A teenager mostly just wants you to get out of the way and leave them alone. But anyway, they don't at least need you to feed them as often. So I said human milk oligosaccharide, and that made me think of this little niece. Anyway, so I'm going to draw this sugar for you. It's you'll be able to recognize a couple of the carbohydrates in it. This third one that I'm drawing is going to look totally foreign to you. Maybe all of it does, actually, since we're all kind of new at this. All right. So I'll just tell you the carbohydrate that we just drew is called L-fucose. And it's weird because it's one of the only carbohydrates that's got the L configuration. If we assigned stereochemistry at its C5, you would see that the stereochemistry is S. So that's opposite what is expected for the other carbohydrates that we've dealt with. What would you say the configuration of this anomeric carbon in blue is? And I'm going to ask you to pay attention to whether the thing coming off the ring at C1 is on the same side of the ring or opposite sides of the ring as the thing coming off at C5. What are they, cis or trans? They are trans. This one is down, this one is up. So what's the right Greek letter for the configuration of the anomeric carbon? Alpha, right? Good. Now, take a look at this carbohydrate here. Which one is that? 1, 2, 3, 4, 5, and 6. Glucose, mannose, or galactose? Okay, I'm hearing a lot of things, so let's review. C2 epimer of glucose is mannose. The C4 epimer of glucose, where the OH on C4 is axial up, that's galactose. So this is galactose. It's D-galactose. And that makes this one here what? Right, how do you know it's not mannose? Because C2, C3, and C4 are all equatorial with a down, up, down relationship. Okay, notice that for this anomeric carbon on glucose, I've used a squiggly line. That means a mixture of alpha and beta anomers. How about the anomeric carbon of galactose? What is its configuration? Check and see, is the thing coming off the ring at C1 on the same or opposite side of the thing coming off the ring at C5? They are cis, therefore it's beta. Okay, good. Now let's describe the glycosidic linkages between the carbohydrates. We've already got part of it here. It's alpha 1, and then what's the other number? 2. So if I wrote L-fucose with alpha 1, 2 in parentheses, and then I wrote galactose, what would need, and then something in parentheses, and then glucose, what would I need to put here? Let's count. 1, 2, 3, 4. beta 1,4. Okay? So this is human milk oligosaccharide. And it's primary source of carbohydrate nutrition for infants, right? This allows us now to talk about something called lactose intolerance. Before I do that, these two carbohydrates, if we get rid of the fucose and just have the D-galactose and D-glucose linked together via a beta 1,4 linkage, that disaccharide is called lactose. All right, so what do you know about lactose intolerance? Anybody heard? Yeah, go ahead.
That maybe the enzymes in your stomach don't break down as efficiently as others.
Okay, enzymes in your stomach don't break it down as efficiently as others, and that's good. What else?
The lactase enzyme to be able to do it. So
Okay.
it just comes from-
Yeah, so I don't know too much about, I don't know a ton, I'm trying to learn. But carbohydrates that you eat complex carbohydrates or polysaccharides need to be digested into their individual 6-membered ring forms in order to pass efficiently through I don't know whether it's the stomach or the intestinal epithelium. I mean, give me a break, I'm not a biologist. Some of you may know some of that. But you gotta break apart or hydrolyze those glycosidic linkages. Now, I showed you in sucrose how this happens with increasing temperature. You need electrons kick down and kick off one of the OHs as a leaving group, and it's got to get protonated as it leaves. That process can be slow because at pH 7, you haven't got a lot of acidic groups present. Enzymes, and the environment of your stomach is acidic. That promotes this kind of thing, but enzymes promote it as well. And there is an enzyme that's called galactosidase. It's actually called beta galactosidase or perhaps lactase. And its job is to promote this reaction where electrons kick down, leaving group leaves, and picks up a proton as it's leaving. That will liberate glucose. Then that will give you the oxonium ion of galactose, which can then become just regular galactose by picking up a water nucleophile. I'm skipping a proton transfer step in the interest of time, but that will free up galactose. And then you can absorb both of them. And your body knows what to do with glucose and with galactose. Now, in the GI tracts of infants that are getting most of their carbohydrate nutrition from human milk oligosaccharide, it makes sense for them to express this enzyme, right? But historically, our human ancestors from thousands and thousands and thousands of years ago didn't necessarily get their nutrition from milk anymore before the domestication of like cows, right? And so the need to express that enzyme was not high, and so most adults no longer had much of that enzyme in their GI tract, which was fine because they weren't getting a lot of nutrition from milk, all right? Well, this is not the world that we currently live in. Like when you go to the store, what are your favorite products to buy? Maybe some of you are not like me, but okay, we got to load up on milk. My sons, goodness, it's hard to tell based on the week. Some weeks we'll go through 4 gallons of milk, some weeks we'll go through 1. Some of them pull the thing where you take all but the last drop of milk so you can technically claim that the jug is not empty and then put it back in the fridge. You guys do that? Yeah. Anyway, so yeah, you've got milk, you got cheese, you got ice cream, a lot of different dairy products. Turns out, I read a book once called A Brief History of Everyone Who'd Ever Lived, and domestication and dairy products, well, domestication of animals happened earlier, but dairy products really sort of started, I think, in Europe as people figured out that they could preserve butter and cheese, preserve dairy products, which you could then eat in the winter when stuff wasn't growing anymore. So there was something of a selective advantage if you could gain nutrition from dairy products. And about the same time, a mutation cropped up in humans in Europe that allowed expression of beta-galactosidase more efficiently. And so to this day, if you're descended from mostly European ancestors, you likely are not that lactose intolerant. If you aren't, you might be. And it's all just related to human history and the fact that at one point in our past, boy, if you could survive the winter on cheese and butter, you were in good shape. So all having to do with hydrolyzing the stereochemistry of a particular linkage in your stomach. Okay. So we want to start looking at larger polysaccharides. Actually, before we do that, on your quiz, I want you to do, if you took notes, you've already done question 3, except note that in your quiz, I wrote the question wrong. Galactose has not an alpha 1,4 linkage, but a beta 1,4 linkage. So if you want to practice drawing lactose again, a galactose linked to glucose via a beta 1,4 linkage, do it. And then I'm going to give you the instructions for another disaccharide called cellobiose. This is 2 glucoses with a beta 1,4 linkage. So go ahead and give that a shot. See if you can draw that. You can do it from the overhead hexagon point of view, or you can do it from the chair point of view, whichever you prefer. Okay, what do you got for cellobiose? You can draw the 2 rings side by side. The thing that's not going to change, if you know that everything's glucose, is the configurations of C5, C4, C3, and C2. So I'm supposed to link C1 of glucose with the C4 hydroxyl via what kind of linkage? Beta. So that's going to be up axial or down equatorial? Up, right? So that would mean that cellobiose should have, let me see if I can draw that just a little bit better. The C4 hydroxyl from the glucose on the right attached to the anomeric carbon of the glucose on the left. And you would write this out from left to right if you wanted to. Glucose, beta 1,4, glucose. GLC is a common abbreviation for glucose that biochemists and chemical biologists use. At the right-hand side, where you've got the anomeric carbon. I didn't tell you whether that should be alpha or beta, so you should just use a squiggly line with an OH on it to indicate that you'd have both anomers. Okay, practice that a little bit. Practice drawing things. You'll get a chance to do that on your problem set. And especially on the problem set where you're going to do sugar caramelization, just be creative with your linkages. Make sure you can recognize them and name them as alpha or beta, and then whatever the appropriate atom numbers are. What we're going to do now is look at some complicated polysaccharides, because nature is full of them. And these are things that you've heard about and things that you eat, and these are on the back of your quiz. So we're going to look at each of these, starting with amylose and amylopectin / glycogen. So amylose and amylopectin are what we call starch. So grains, potatoes, other carbohydrates. My favorite carbohydrate source, aside from cookies, is like, I'm a cracker person, so I bring in my lunch every day, crackers and cheese, because it's easy and delicious. So let's look at what kinds of sugars are linked to what other kinds of sugars, and then what the nature of the linkage is. Amylose is a straight chain of, these are all the same carbohydrate. What is it? Is it glucose, mannose, or galactose? Glucose, good. So we'll call that GLC, glucose. Now, what's the nature of this glycosidic linkage? What would you call it? Alpha 1, 4. Good. And how about this one? Also? And that one, and that one, and that one. So in amylose, which is a simple form of starch, the linkages are all the same. Why would it make sense for nature to do that? Yeah, why would it make sense for nature to do it all the same? It means you only need one kind of enzyme to build the molecule, but it also means you only need one kind of enzyme to hydrolyze it. And it means that you can use the same enzyme probably to clip off one sugar and then the other and then the other and then the other without needing different enzymes along the way. This process actually starts in your saliva. So what I should have done as an activity, but you can do, is go home and find some stale saltine crackers. Does that sound like a fun thing? No. Okay, don't buy saltine crackers because they're disgusting, but that's sort of the point. So buy a saltine cracker and stick a cracker in your mouth, get a little bit of water and chew it up, and then just swish it around there for a while. Like a baby. If you want to feel like a small child, you can start, if you want, you can start drooling it, and you can rub it in your hair too if you want, all right? What you should notice is at first it will taste like a cracker. As you swish it around in your mouth, it will start to taste sweeter. The reason it's starting to taste sweeter is because you're starting to hydrolyze glucose molecules off the end of those starches. Now, glucose doesn't actually taste as sweet as table sugar. It's not as, it doesn't, there's a sweetness index for sort of how things are, and table sugar is pretty high up there. Glucose a little bit less. So it's not going to taste like you took a spoonful of sugar, but you will start to taste some sweetness, and that's because the enzyme's starting to clip those off. Let's look at amylopectin. It's almost exactly the same as amylose, but there are branch points. So let's look at one of these branch points. What is the configuration of that glycosidic linkage? You may have to tilt your head to see what the carbohydrate on the right is, what its configuration is. What do you think it is? It's alpha, because it's on the opposite side as the C5 substituent. What's the number over here? 6. So that's an alpha 1,6 linkage. That's a branch point. And there's the more complicated starch called amylopectin has a lot of these. In amylopectin, there's a alpha 1,6 branch point basically every 25 sugars. In glycogen, which is how you store glucose in your liver, there are also alpha 1,6 branch points, but they happen much more frequently, every 8 to 10 carbohydrate units. Okay, so we'll continue this discussion next time. And what we're going to do is talk about how small things proceed, great things proceed from that which is small, because you can't digest fiber, and we'll talk about that. All right, see you tomorrow.